Welcome back, physicists. I am sorry that I'm not with you today. Zeke was not feeling well this morning, so here I am at early morning recording this video so that we don't just have to pause moving forward. So, you guys have lucked out. The lab that I asked you guys to finish, if you haven't finished it yet, you're in luck. I will be collecting it tomorrow upon my return. So, getting back into things then. Hopefully there's one person in charge of pausing, resuming, and things like that as we go through this. But the last thing that we have in our notes, once you grab them out, is this statement. And there might have been a triangle after it. We'll deal with the triangle as need be. But we had a lab dedicated to measuring mu sub k and mu sub s, which recall are the coefficients of friction, kinetic and static for k and s. Now, when we measure these things, I think you guys came out with values close to 0.6 the other day, which is awesome. Just a couple things I want to hit on. When we do this, to get great values, we require a few things. And easy to kind of list these out: dry and perfectly clean. That's like the two big things. Dry and perfectly clean surfaces. The reason that we require the dry surface is that the cohesive properties of water can kind of impact those things, or any liquid for that matter. If you would like, I would encourage, just to get a kind of feel for these, there is table 2 on page 132 if you want to check it out. Table 2 on page 132 winds up showing a few of the different coefficients of friction for a variety of materials. Cool. Now, we are going to be working through a couple of problems today, and you will have time to kind of finish the rest of them, or at least attempt them, hopefully finish them. But we're going to be working along on a worksheet. So right off the bat, as we go through this, I just want to talk about notation stuff. You guys should have, or if not, if somebody would please pass out the worksheet for today, it should look something like this. And this is the first problem on here. And I'm actually going to undo that and put it up on top so that it looks a little bit nicer in the notes, where our entire focus today is going to be on just solving some problems. So let's go ahead and take a look at this first page. Couple things I want you to notice. On the very top, we do have the equation for the force of friction that's static and kinetic, that is based on two things. Only ever based on the normal force and the coefficient of friction that we're given. So here we go. You're going to get to admire a little bit of my artistic ability, and we'll just jump right in. So here we go. We are looking at this first problem, and we're going to play around with it, but we have a child that's dragging a box across the sidewalk. And we're told that for whatever reason, it's at this exact speed, which means, notice, constant velocity, really important idea. Acceleration, I think we know it. Now, if we pull at some angle, don't care what the angle is right now, and the coefficient of friction between, kinetic friction between the box and pavement is that, I want us to find the horizontal component of the applied force. Now, this picture is there to help us kind of make sense of it, but I do want to take the time as well just to make sure that we can see, hey, a free body diagram, possibly even drawn on this box, but I'm going to do mine below, could help to make sense of it. So let's do that. Here I am, or there's a box rather, and we have a few things going on. First thing right off the bat is that I know that gravity pulls downward on this box, and luckily we're on a flat surface, but because I'm not going to use gravity itself, I'm going to identify this force that's going perpendicular to the ground. And we'll even use a dash. No, I'm not going to use a dash. I know that I have the normal force. So here it is, my normal force. It pushes up. Beyond that, we have friction that's fighting me. So here's friction going this way, the force of friction that is kinetic. And then our last little piece, and I'm going to do this one in a couple different colors, is we have the force that the child pulls at. And we don't know exactly what the angle is, but I'm going to just say FC for child. Okay. So as we look at this, the reason I'm going to use two different colors, what I want to be really clear is that we have two different forces that result from this child pulling. We have the force that the child pulls in the X direction. That's that purple one. And then in this green, we're going to have the force that the child pulls in the Y direction. Now, on my original, I don't have all of this listed, everything except the Y value, because notice we're only looking for the horizontal component. We are looking for this purple one right here. So, good habit to go through. I want to just make sure that we have our known information here. Okay, let's cook. Right off the bat, I know that the mass of this box is 1.56 kilograms. I know that the velocity is constant, and I'm not even going to write down the velocity, I don't think, but what I will write down is I know that the acceleration is 0 meters per second squared. If I have a constant velocity, it's never changing. So let's see, we have that. I know that gravity is negative 9.8 newtons per kilogram, just our nice constant value. And then the only other thing that is worth writing here is we know that the coefficient of kinetic friction, which is mu sub k, is equal to 0.65. That is all of our known information in this problem. We are asked, using this, to find, and I'm going to write it underneath just so I can use this workspace, we're asked to find the force of the child in the X direction, or the horizontal component, if you will. So let's dig into this. All right. Well, getting started is always the hardest part, but as long as we remember a little bit of what Newton, has taught us, we should be okay. Here is, I'll go back to purple. Here is all the work in the equations, and I'm going to make that so much less bold. I hate it. Okay. For this problem, I know that the acceleration is 0. And any time that we're told that the acceleration is 0, it is a good idea to start thinking about net force, because I know that it must be balanced. So here we go. I know that the net force acting on this is just the sum of all the forces. So let's just check it. I assume that the child is pulling in the positive direction. So we'll say F sub c of x, the force of the child in the x direction. And I'm going to minus, because I know it's counteracting this, the force of kinetic friction. Okay. For this, remember that this is equal to 0, and we know this because acceleration is equal to 0. I'm not accelerating at all, which means immediately we know that the force of kinetic friction is exactly equal to the force that the child is exerting on the box. So I'm going to switch this around. Instead of having kinetic friction on the left side, I'm going to have the force of the child on the right side. But what I've done here is I've just added the force of kinetic friction to both sides. Okay, we've got it. Now, in doing this, I don't know the angle the kid pulled at. I don't know the magnitude of the force that they pulled at, so I can't do any fancy trick stuff here. However, if we look at this, the force of the child in the x direction, I know it's exactly equal to the force of friction that we're dealing with. And luckily for me, I know that the force of kinetic friction right here is just simply going to be mu sub k times the normal force. Now, as we go through here, what I notice immediately is, man, well, we didn't really have the normal force listed. That was not something that we were given right off the bat. But that's okay. I know that the normal force is just the force of gravity perpendicular to our surface, which in this case, if our surface is flat, which it is, we have the easiest possible job. I know that the force that the child exerts is equal to mu k times the normal force of this. So instead of writing Fn again, I'm just going to say, well, the normal force is just negative mass times gravity. With these values, it's just a simple calculator problem. I know that the kinetic friction's coefficient is 0.65. The mass that we're dealing with is 1.56, and I snuck in the negative there. And that's kilograms, and I'll play the units underneath. And gravity is 9.8, or negative 9.8 rather, newtons per kilogram. By doing this little unit game, I see that my kilograms cancel. I'm left with newtons, which is exactly what we're after. And a little bit of calculating away, we should get that the child's force in the x direction seemingly is approximately 9.9 newtons. Boom. I would encourage to write in your example, write this in a specific context. So I'm not going to write it right now, but I would say that the child pulls the box in the x direction with a force of 9.9 newtons. Easy. Piece of cake. Okay. From this problem, you can now do number 2 on your assignment. So this is similar to number 2. Okay, we're going to hold on to that. Now, moving forward, and this also turns out similar to number 3. So from this example, you guys should be able to do problems number 2 and number 3 from there. Cool. Where things get a little tiny bit more challenging is when we get to problem 5, it seems. And I've lied directly to you. There's nothing crazy going on here. We don't have any wonky angles happening. So, what I would like to do then is a super short video. We have one example. I want somebody to go ahead and pause this now, and I want you all working with your neighbors to try to work through number 2. And as you're doing so, I will also do it, but I'm going to pause it. I want you to pause the video now, work through number 2 where we're dealing with, what is it? We're dealing with a 9 kilogram crate. And I want you to solve that one. Start working it, pick somebody to come up and pause the video, and you will see a detailed solution for problem 2 that we'll be able to look at and compare in 5, 4, 3, 2, 1. And here is my detailed work. Going through, one thing just as a reminder that I do that you may love or hate, I don't know, depends on the person I imagine, is I don't plug in any values until I'm at the very end. So what you see happening is I know that I'm not moving the box yet until I apply this much force, and then it finally starts to move. That means for us that the net force is 0. So I add the friction to each side. I just know that the force of friction is mu times the normal force. And then I'm just going to solve for the mu sub s. So I'll divide both sides by the normal force, where I know that the normal force can be replaced with negative mg. We plug in, and we have a solution. So nothing hopefully too crazy. What I want you to do with the remainder of class time is I want you to work through problems 3, 4, and 5 on the examples. And when you're finished, 1, I want you to note any questions that you might have. But 2, I also want you to, if you finish on time and early, see if your classmates needs help, or and work on anything academic that you have. Cool. I will be back tomorrow, and we will start making the jump into the second dimension. So, see you guys tomorrow. Hopefully you found this helpful, and I want you to work through the remainder of these problems.